In this video, we will see detailed review of these small, compact, and amazing LoRa transceiver modules. RYLR998. Manufactured by Reyax Technology. We will see brief introduction to LoRa technology, module specifications, AT commands configuration guide, and we will also see one small DIY project using these modules. So, let's get started. Hello all, welcome to Make 2 Explore channel. First of all, thank you to all our subscribers, viewers and supporters. In this video, we are going to unbox and review a product, LoRa transceiver module, RYLR998, which is manufactured by Reyax Technology. We will know more about them in later part of this video. So without any delays, let's get started. Before going forward, let's first see about LoRa. What is mean by LoRa? So, LoRa is a wireless communication technology that offers long-range, low-power, and secure data transmission for machine-to-machine and IoT applications. It is same as other wireless technologies which we used in our day-to-day life, like Wi-Fi, Bluetooth, Zigbee, etc. But there is a difference in their range of coverage. Let's see this diagram. So here are few commonly used wireless technologies, like Bluetooth, which ranges up to 30 feet. Wi-Fi ranges up to 200 feet. Zigbee ranges up to 1000 feet. And LoRa can be ranges up to 10 kilometers. So, in technical terms, LoRa, which means long range, is a physical proprietary radio modulation technique. It is based on spread spectrum modulation techniques derived from chirp spread spectrum (CSS) technology, which has low power characteristics like FSK modulation, but can be used for long-range communications. It was developed by company named Cycleo, based in Grenoble, France, and later acquired by Semtech, the founding member of the LoRa Alliance. Semtech means Semtech Corporation, is a supplier company of analog and mixed-signal semiconductors. Since LoRa is used for wireless communication, there will be communication between different LoRa nodes. So, eventually, another very important concept comes into picture. The networking. Network of LoRa is called LoRaWAN. Means low power, long range, wide area network. LoRaWAN defines the software communication protocol and system architecture. These are nothing but standard set of rules with which we should communicate using LoRa technology. So, who manages this protocol? The LoRa Alliance. LoRa Alliance is an open, non-profit association of companies with over 500 members who supports, manages and promote the global adoption of the LoRaWAN. This alliance is dedicated to promoting the interoperability and standardization of LoRaWAN. Okay, these all are basic introduction about LoRa and LoRaWAN. But what is actual difference between them? Let's see. So, LoRa itself is the semiconductor, physical layer, with modulation technique that enables communication with very low power consumption. It's a semiconductor chip. So you can see here in LoRa stack, it is a physical layer, consists of Semtech's LoRa modulation engine, and these all are different standard bands of frequencies for different countries. Whereas, the LoRaWAN is the MAC layer, that is, the software, which is put on the chip to enable networking. It refers to a network protocol. In a nutshell, LoRa and LoRaWAN together defines a low-power, wide-area networking protocol designed to wirelessly connect battery-operated things to the internet in regional, national, or global networks and targets key Internet of Things requirements such as bi-directional communication, end-to-end security, mobility, and localization services. As we mentioned earlier, LoRa uses license-free, sub-gigahertz radio frequency bands. Hence, each country, or region, uses different frequency bands. Like Europe, North America, South America, Asia, India, etc. In India, LoRa operates at IN 865 band. Means at range of 865 to 867 MHz, typically. These all specs are according to LoRa Alliance standard. Since these all bands are unlicensed, anyone can freely use any of them without paying or having to get a license. LoRa does supports long range, but there is one catch, or you can say trade-off. Here, in this diagram, you can see LoRa has a wide range, but comparatively very low bandwidth. Data rate for LoRaWAN ranges from 0.3 kbps to 50 kbps per channel, depending upon the spreading factors. But despite the fact, these data rates are more than enough for exchanging data from sensors, actuators, and tags. This makes LoRa as pivotal technology in IoT applications. LoRa has vast range of applications in different areas, such as industrial control, healthcare, agriculture, smart cities, home and buildings, environment, net metering, supply chain logistics, and so on. So, here you can see different scenarios of LoRa-based solutions ranging from smart cities with gateways and cloud-based network controller with number of nodes. Connected infrastructures, traffic control, garbage management, sanitization and well-being, etc. Let's see one scenario for which we will try to provide solution using Reyax LoRa modules. Sometimes, where there is very low coverage of cellular services, like a remote villages in underdeveloped countries, deploying IoT-based solutions in such areas is very challenging task. Here LoRa technology can play important role. Let me show you one scenario which we can implement as solution using LoRa. Suppose there is a farmer whose multi-acres of agricultural land is in village or in area which comes in shadow region C, means area which have no connectivity of Wi-Fi, GSM, cellular, or Ethernet. This region can be 5 to 10 miles away from bigger cities or towns where good connectivity to internet is available. Now suppose there is a greenhouse in area C. We need to monitor its parameters like temperature, humidity, soil moisture, etc. from another distant location, like from anywhere in the city or state. So, how we are going to achieve that without Wi-Fi or internet connectivity? So you can see, this particular area comes in these type of regions where signal coverage gets weaker and weaker from surrounding cities. These are shadow regions. Due to very few subscribers population in such areas, cellular companies also hesitates to deploy any dedicated infrastructure for them. Therefore, here comes the usability of LoRa technology. We can implement system which connects any monitoring or controlling system of greenhouse to the LoRa transmitter, which will send the corresponding data to the LoRa receiver or gateway, which will be at any town A or B. Here, at these cities, at locations A or B, we can use ESP8266 or any other Wi-Fi enabled controller interfaced with LoRa receiver module to receive the data. So, once we get that data via LoRa to A or B, we can now send that data to cloud. Hence, it will eventually get shared and can be accessed from anywhere in the world. This is just one hypothetical example of application of LoRa technology. LoRa can have vast range of applications. Okay, now, we will see detailed block diagrams and circuit diagrams of the project. Here in this block diagram, there will be a transmitter and receiver sections. In transmitter part, we will connect node MCU ESP8266 to LoRa module RYLR998 through serial interfacing. And on receiver side, another ESP8266 is connected with Reyax LoRa module, which will act as a LoRa receiver or gateway. Here transmitter side sends these environmental parameters readings to receiver through LoRa at regular interval of time. This receiver receives those readings and upload it to cloud, which then can be accessed by farmer from his cell phone or PC, so he can monitor the greenhouse. Also, at greenhouse, we have implemented basic level automation for irrigation system. Therefore, as soon as soil moisture level falls below certain level, water pump will get start and it will circulate water to the plants. All this communication of LoRa can be achieved using this LoRa module RYLR998, which is manufactured by company named Reyax. Let's know more about them. Reyax is a Taiwan-based electronics and semiconductor manufacturing company, which mainly works in wireless communications, and IoT domains. Here is the website of Reyax. You can see they have wide range of products categories depending on technologies like cloud, Wi-Fi, Bluetooth, LoRa, RF, NB-IoT, 3G, 4G, LTE, GPS, antenna devices, sensors, and many more. Although this video is not sponsored, Reyax do send us sample of their LoRa and RFID NFC receiver modules for testing. This is RYLR998 LoRa transceiver module. In this video we will see detailed review of this LoRa module. So, without wasting time, let's get started and unbox the shipment we got from Reyax. We will now unbox the Reyax shipment. They have sent us this shipment through FedEx, which got delivered in a relatively short time. You can see all products are packed in bubble wraps and plastic enclosures with anti-static bags. Packaging was very good and properly labeled. Here is the LoRa module, RYLR998, which we are going to test in this video. Packed in this plastic box or enclosure. Good for protection against any handling damages during shipping. Let's open it. Oh dear. Look at this, how tiny and compact it is. Simply amazing. This is LoRa transceiver module. Means it can transmit as well as receive LoRa data. Reyax also sent us one more product for testing, which is their NFC RFID module. We will make another dedicated video tutorial for it. But before that, in this video, let's see more detailed technical information about their LoRa transceiver module. To know more about this module, let's check out its datasheet. Here is the one. You can see, in the title itself they have explained most of the important features of this module. Like, it supports UART serial interface. Frequency range is 868 to 915 MHz. It has antenna transceiver module. Then here, in product description, it says, this module is a long-range modem that provides ultra-long-range spread spectrum communication and high interference immunity whilst minimizing power consumption. It features Nuvoton microcontroller and Semtech LoRa engine on chip. Here is that chip. Then, as we mentioned earlier about inference immunity, this module features excellent blocking immunity. Smart receiving power saving mode. Most importantly, this modem can easily configured and controlled by AT commands. This module can be used in several applications, mainly in IoT devices, mobile equipments, home security systems, and also in industrial monitoring and control systems. Module is under testing for FCC and NCC certification standards. Now going forward, let's see its pin description. So, there are 5 pins. Ground, transmit, receive, reset, and VDD power. Reset is active low. Then down here, these are the timing diagrams of different signals on powering up and powering down. Keep note that you have to keep TX and RX pins low before powering up and powering down. Then next, here is the block diagram of RYLR998 module, which consists of MCU, LoRa engine, transceiver section, and crystal oscillator. Here they have shown how you can connect this module to other development boards like Arduino. Now, let's see electrical specifications of this LoRa module. So, you can see, this module can be powered through 3.3 volts power. Another important specification is input-output pins rating. Here note that I/O pins means transmit and receive pins of this module are 3.3 volts tolerant, not 5 volts. So, you need to use logic level shifter or resistor network if you want to interface this module with 5 volts compatible TTL devices. Okay. So, This was all about specifications and electrical characteristics of Reyax LoRa module. Now, let's see how to configure this module using AT commands. You can find this AT command guide on the website of Reyax. We will share the link in description box. This is sequence of commands for first-time setting of RYLR998 LoRa module, like address, network ID, frequency band, parameter mode, etc. In this document, you can dig out more about each command in detail. Further, you can set UART mode, sleep mode. You can also change communication baud rate if you want. Likewise, you can use this AT commands guide to configure the LoRa module. So, let's see how to do that practically. For that, you have to connect RYLR998 module with either Arduino or FTDI serial to TTL adapter module, like shown in circuit diagram given. Let me show you. Here, as we mentioned earlier, in specifications, TX and RX I/O pins of this LoRa module are not 5 volts tolerant. So, for Arduino Uno or Nano, we have to use resistor divider network to power down the 5 volts to 3.3 volts logic level. Or, you can also use logic level shifter module, as shown here. Then next, if you have this kind of USB serial to TTL adapter module, then you can connect like this circuit diagram. But, just remember to put this jumper on 3.3 volts logic. Okay, once you connect the RYLR998 LoRa module to PC through serial interface, it will get detected in your PC as a COM port. You can verify that from Device Manager, like this. Now, open the Arduino IDE. Go to Tools. Port. Then select correct COM port. Then, open Serial Monitor. Here, keep new line and carriage return option enabled and then set the baud rate as 115200. Open AT commands guide side by side in another window. Here, as they given, it is required to key in enter or /R and /N in the end of all AT commands, which we have set here. Then, if you want to query about the current setting value, then you have to append question mark in the end of commands. And it is required to wait until the module replies OK so that you can execute the next AT command. Now, see here, if we type AT in this field and hit enter or press the send button, then, if LoRa module got properly connected and working, then it will give us response as OK, let's see. Here, like this. So, we can deduce that we are now ready to configure the LoRa module. Let's configure transmitter LoRa module first. We will use sequence given here. Like, first, address. For that, use AT plus address to set the address. It is regarded as the identification of transmitter or specified receiver. Now, if I give question mark at the end of this command, like this, then we will get response of its previously configured value, which is 0 by default. Since we are configuring this for the first time. Down here, in documentation, details of address command are given. We can see, you can set the address, ranges from 0 to 65,535. Let's set it as 126. So, command will be like this. AT plus address equals 126. You can also verify it by giving query command, which is correct. OK. In the similar manner, you can execute other commands from that sequence. Let's see second command. Here, the second command is setting of network ID. As they says here, to set the ID of LoRa network. This is a group function. Only by setting the same network ID, the modules can communicate with each other. If the address of specified receiver is belong to different group, it is not able to communicate with each other. So, we need to keep similar network ID for transmitter and receiver. Let's see this in more details. Down here, you can see, we can set network ID ranging from 3 to 18. Okay, default network ID is 18. So, we will keep our network ID as 7. Run this command. Is it got set? Yes. Okay then, next config is band. Means RF frequency. Center frequency of wireless band. The transmitter and the receiver are required to use the same frequency to communicate with each other. Let's see this in more details. So, here you can see the standard syntax of this command. Here RF frequency is in Hertz, and it is to be set as parameter. So we will use 868 MHz band, which we have seen in LoRa Alliance standards, IN 865, for India. So, therefore, command will be like given here. Now, we can verify it using query command, which gives us response as OK. Then, next command is parameters setting. Here we set the RF wireless parameters. Transmitter and the receiver are required to set the same parameters to communicate with each other. The parameters are as given here. First, the spreading factor. The larger the SF, better the sensitivity. But the transmission time will take longer. Second is bandwidth. Smaller the bandwidth, better the sensitivity is. But the transmission time will take longer. Third is coding rate, which will be fastest if set as 1. And last is preamble code. Let's see this in detail. Down here in command syntax, you can check values of all parameters. We will use this command, which is explained here. Copy it and paste it in the command field. Like this? Okay, so in this way, you have to configure receiver LoRa module also. Next important command is send command. Let's see the syntax. Here, you have to put the address, payload length of maximum 240 bytes, and then data in ASCII format. Here is the example. Okay, now, let's see LoRa networking in brief. So, you can see here, in this diagram, there are two different LoRa networks. Network 1 and Network 2. Each node and network should have unique address. Nodes with same network IDs can talk to each other. Also, LoRa frequency band should be correct as per standard frequency for respective country or region. Here note that nodes from different networks means with different network IDs cannot communicate with each other. So, in this project, we have configured both transmitter and receiver with same frequency band, same network ID, and different addresses. Therefore, we can say, for proper LoRa communication between two nodes, LoRa trans receiver device should be configured with these three parameters, as shown here. Band, network ID, and device address on network. Okay, this was all about configuration of LoRa modules to work as transmitter and receiver. In our DIY project using these Reyax LoRa modules, we will include the sequence of LoRa module configuration commands in the setup function itself. Therefore, no need to configuring LoRa modules separately. Okay, now, we will move forward and see the main circuit diagrams and interfacings of the project. So, there will be two main circuit diagrams for this project. One is of transmitter section and second is of receiving part. We will see them one by one. Okay, this is circuit diagram of transmitter node, consist of all these components like node MCU, Reyax LoRa RYLR998 module, DHT22 sensor, soil moisture sensor, relay board, and OLED for displaying some sensor parameters locally. This design is just for demonstrating how we can exchange data from remotely unconnected field, which located out of coverage area of cellular and internet services, using this amazing wireless LoRa technology. Okay, now, let's see receiver part. This is the receiver, or, you can say, gateway between remote node and cloud. This circuit consists of node MCU ESP8266, which is connected to Wi-Fi, as well as interfaced with this LoRa transreceiver module to receive LoRa data. It will relay whatever data received from LoRa transmitter to the cloud via internet. Also displays it here, using this OLED display. Connections in both the diagrams are shown with color coding, so you can easily trace them. We will share these schematics on GitHub. Now next, we will see codes, or programs of transmitter and receiver. These are source codes. Let's see them one by one. But before that, if you do not interested in lengthy explanations of these codes, you can just skip it and jump to this timestamp to see the demo of the project. Okay, so moving forward, this is the transmitter node source code, from which we are going to send different sensor readings to receiver node. Whole source code is properly commented. I will just walk you through the important sections of the code. In the beginning, these are LoRa transceiver configuration parameters, which we have seen earlier, like LoRa band, network ID, address, etc. We will include these in string of AT commands in setup function. Okay, then next, here we have included all important libraries. Here, these are for software serial communication, OLED display, and DHT sensor. Then next, define objects of software serial, and then set the display of 128 by 64 pixel screen size. This is logo bitmap, byte array. Then next, define DHT sensor related stuff and the variables for sensor parameters. Then, here is the setup function, where we will first initialize the serial communication baud rates. Then, these are serial print statements to send AT commands for configuring LoRa transreceiver module. This sequence of commands will run at every startup. Only once. Hence no need to configure these LoRa modules separately. Then moving forward, we initialize DHT sensor, OLED display, and print startup message. Then next, this is read sensor function for taking readings of temperature, humidity, and soil moisture percentage. Then moving forward, this display data function is used to display the sensor readings locally on OLED display. Then down here, the process data function creates the string of data to send as an AT command. So, this send data function is used to send the data string created in previous function. Here you can see the address of it. You can change these values as per your configuration. And then, finally, in main loop, we use mils function to create small interval between data posting. And then we will call all these functions. Alright, this was all about code of transmitter node. Now, let's see code of receiver node. Here, we are receiving data coming from LoRa transmitter node via LoRa serially. And then, we upload that data to Blink Cloud. So, here we have initialized some Blink Cloud credentials, you have to replace them with yours. These credentials are those which you will get when you create Blink template on dashboard of Blink Cloud platform. How to do that? Not the topic of this video, but you will find several tutorials on YouTube for doing that. You can check them out on your own. Then next, in order to connect to the cloud, we need to connect with Wi-Fi. Here, we will program Node MCU to connect to our local Wi-Fi network, whose credentials you have to enter them here. Then next, most of the code is same as of transmitter. Here is the check serial function, used to read the incoming data. By the use of this read string method, you can see, this is data receiving format. Means, we receive data string, which consists of plus RCV, then address of sender, then length of data, then data itself, after that, RSSI, signal strength, and signal to noise ratio, SNR. Then moving forward, we pass this incoming data string to function named getValue, which we have defined later. Let me show you. Here, this is the one. It is used to parse the data string and separate data, sensor readings, from whole string. This send to cloud function is used to upload whatever data we received from remote field LoRa node to the cloud, the Blink cloud, which then administrator farmer can access from anywhere in the world on his mobile app or laptop. This display data function displays data on OLED display. And finally, in this main loop, we run blink and timer functions to regularly fetch data and upload it on the cloud. Okay, alright, this was all about coding part. We will share these code on GitHub. Links will be shared in description. Now let's see the demo of this project. So, you can see here, we have assembled this mini project, LoRa-based greenhouse monitoring system. You can refer circuit diagrams for more details. Let's check out all the components one by one. This is transmitter section. This all components forms transmitter node, which consist of node MCU ESP8266. Then this is OLED display module, DHT22 temperature and humidity sensor, Reyax LoRa Module. This is soil moisture sensor. Here, these containers are with wet soil and dry soil for testing purpose. This is 2-channel relay board to drive the motor pump or this fan. This is USB power bank used to power the ESP and transmitter section. To power this DC fan we have used this 7.4 volts LiPo battery. So, this all forms transmitter section, which will be at remote greenhouse field. Then next, here is the receiver section circuitry, which includes ESP8266 board, OLED display, and Reyax LoRa module, which will work as a receiver. This receiver section will be powered by this another USB power bank. This is fully assembled circuit. Now, we will power on the transmitter. Okay, so first, it will fetch all the sensor readings. Means, temperature, humidity, soil moisture, etc. And then display them on OLED display, like this. So this was transmitter section. Now let's power on the receiver and check whether we are getting the readings via LoRa or not. So, you can see, receiver is starting. And we are getting all the readings. We are receiving all the parameters through LoRa. Simply amazing, right? Okay, I will now show you the Blink Cloud dashboard. The receiver ESP is connected to internet via Wi-Fi. So, it is uploading those greenhouse received sensor readings to the Blink Cloud. And hence, we can check and monitor them from anywhere using Blink mobile application. Let's see. So you can see, here is the Blink app showing project name. Let's open it. Here is the dashboard of our project, showing all the widgets of sensor readings of greenhouse. You can also compare these readings for verifying whether they are showing correctly or not. Okay, now, we will check the simple edge level automation which we have programmed for irrigation system. In this automation, if soil moisture level falls below 40%, water pump will get start. And it will provide water to the plants until soil moisture level rises above 60%. We can also use automation and notification alerts facility of Blink app, like shown here. Okay, so this was all about demo of the project, LoRa-based greenhouse monitoring system. We will share all the codes and circuit schematics on our GitHub page, links will be given in the description box. In next part of this project, we will try to test the range, or coverage of these Reyax LoRa RYLR998 modules. We will keep the transmitter section at fixed location and move the receiver away for distance of 1 to 5 kilometers. And check how much distance these modules can cover with good LoRa reception. Stay tuned for more updates. If you face any difficulty in replicating this DIY project, feel free to ping us on Telegram, or you can also send us email at info@theratemakeToExplore.com. We would be happy to help. Thank you.